recording. Okay, I just started recording. Okay, anyway, so this makes it 0. Okay, so just for the recording, I forgot to record, so let me just tell you this. So we defined something called the minor of the coefficient, which means that to find the minor of Aij, you delete the row I and column J, and then you obtain a submatrix which has size n-1 times n-1, and its determinant is called the cofactor. And here we did an example, okay? So we tried to compute the minor of A22. We erased this second column and second row, and we got this matrix here. Now its cofactor is a sign times determinant of this minor. Okay, so how is this sign determined? It is -1 to the power whatever these numbers are. You sum them, you get this. Okay, it's an interesting formula. It will help us compute determinant in another way. Okay. So here we're seeing the relation between these cofactors and the determinant. So to find the determinant of a matrix, what we do is we take any row. Okay, so we take any row, for example, row I, and take the first element in row I. Okay, let me do it. So we have a matrix here, A11. So here we have the ith row, a I2, and a IN. Okay, so we have such a matrix. So we have other entries here, and finally a NN. So we take here, we choose the ith row. Okay, this row. Then what do? We start with the first element here, which is this guy. We write it here. And then we compute the cofactor corresponding to this element, capital AI1. Okay, so if you remember the definition, you compute it in this way. So it is -1 to the power of something times the determinant of a matrix, and this matrix is the minor matrix. Okay, so we will do examples, and you will see it. So this is the first entry, and then you carry on with the second element here. You do it for the second element, okay, and then you multiply it with its cofactor, and you add them, and you carry on all these operations until you go to the end, okay, end of the ith row. That will give you the determinant. So I don't want to do this for the general case, but let's look for the 3x3 case, why this formula gives the correct answer. Okay, any questions? Geliyor mu arkadaşlar ses ve görüntü? Evet. Okay, so let's just do it for the 3x3 case. So I will zoom in here. So let me choose this one. So A11, A12, A13, and A21, A22, A23, A31, A32, A32. So I'm trying to compute the determinant of this guy, okay? So I'm trying to find the determinant of this. Now, how do I do that? Now, if you remember the formula, so we had the Sarus rule, right? Sarus rule. Now, Sarus rule says what? Sarus rule says this. Okay, let me write down the Sarus rule here. A11, A21, A31, A21, A12, A22, A32, A13, A23, and 8, 3, 3. And you repeat the first column. And you repeat, then you repeat the second column. Let me know if I make a mistake anywhere, okay? There are a lot of numbers here. 822 and then 832. Okay, so then what do we do? So we go this way, and these are coming with the positive sign, okay? So these three terms. So let me write them. So A11 times A22 times A33. Then the second one is again a plus sign. A12, A23, this is like 3, A23, A31, and then the third one is A13, A21, A32. Okay, these are coming with the positive sign, and then we go with the those ones with the let me choose this negative sign. So this one's coming with a negative sign, this one coming with a negative sign, this one coming with a negative sign. Okay. So let me write those. Minus A13, A31, and then, wait a minute, let me write them in order. A13, A22, and then A31. And also for the other one, A11, A23, A32, and what is the last one? Minus A12, A21, A21, and A33. Okay. To compute the determinant. So this we have already learned how to compute the determinant of 4x4 matrices, but I think I never gave you an example. So we already know it. I will do an example about it. Okay, and this method also works for any n by n matrix. Okay. So using this method, you can compute the determinant of any n by n matrix. Okay, so now this is the Sarus rule we have seen before. Now let's write this in a different way. So let's just look at the whole expression here. So I'm going to write it in a different way. So I have A11 in A11 parentheses. Which terms do I have? I have this term and this term. Okay. So what are those things? A22, A3. If I don't zoom in, I can't write very good. A22, A33 minus, what is the next term? This one, A23, A32. A23, A32. And the next expression, let me look at terms with A12. So I have this one and this one, which is, okay. Let me try to write it with a minus sign. So the minus sign will come clear. So I have with the minus sign this part, right? These two terms, which is A21 and A33, minus I have these two terms, A23 and A31. Okay, so this is, and what is the final term? So these two terms are the final terms. Let me write them in A13 parentheses. In A13 parentheses, I have A21, A32 minus A22, A31. Okay, now, so this is kind of too much work, but we're getting close. So let's look. So what is this thing? What is this thing? So A22, A33 minus A23, A32. Well, if you look at, let me just for the moment erase these things. So if you look at the determinant of this part, this 2 by 2 thing, you will see that it is exactly this term. Okay? So determinant of this one And the determinant of this one times minus 1 to the power 1 plus 1 is basically the cofactor. Okay, so I can write this a 1 times okay, let me do one more step. So this is the determinant of a22, a23, a32, a33. And let's look at the second one. What is the second one? Second one is, I will write it a plus sign, a12, and what is this? Minus 1 to the power 1 plus 2. And let's look at, let me erase this thing. Let's look at this part. So what is it? It is basically, if I remove these two terms, and if I compute the determinant, I get this times this minus this times this, right? So it is the determinant of these two things. A21, A23, oops, and then A31 and A33. Okay. Oh, I don't have a space, so let me erase here. So the final thing is this term. So I also have this term. So this is basically A13 times A13 times minus 1 to the power 1 plus 3, which is 1, times these terms, A21, A22, A33, A31, and A32. Okay, so what is this thing here? This thing is basically, let me erase this. This thing is basically the determinant of the matrix where you erase this part and this part. Okay, so you get this part, the determinant of 2 by 2 matrix. Sorry, too much computation here. But finally we got the result. So what is, so let's go back. So what is this thing? So this is really the cofactor of A11. So it is the capital. So I can write this whole expression here, the whole thing here, as A11 times the cofactor of A11 plus A12 times the cofactor of A12, capital A12, and plus A13 times the cofactor of A13. So this is the expansion of the determinant using the first row, okay? Now we will do an example. I think you will understand better with the example. But this shows that the formula, at least it holds for 3 by 3 matrices. Here we're just expanding in the first row, okay? So I will do an example. Okay, so the the best way to, so here you can you can expand expand the matrix. You can expand the matrix in any row, okay? So what is the best way to expand? Well, the best way to expand, if you look at the formula here, the best way to expand is choosing a row where you have a lot of zeros. Okay, so if there are a lot of zeros, then you don't need to compute the cofactors, because computing the cofactors takes time for large matrices. For small matrices, it's easy, but for large matrices, computing the cofactors are not easy. So let's go this example. Let's go to this example. So how does this method works? Okay, I can do it in different ways. The first way, let me try to compute this by expanding in the first row, okay? So let's look at this row. So if I do that, I will get 4 times, okay? So I'm computing the determinant here. 4 times minus 1 to the power, the position of the first entry, 1, 1. Times, I'm deleting the first row and the first column, and I get a 2 by 2 matrix. Okay, this is the first entry, so I will compute this determinant. And next is next term is it is plus this. I look at the second entry here, which is 3. The position of 3 is -1 to the power first row and the second column. And now what I do is I delete this column and this row, so I get a 2 by 2 matrix, 5 and 6. Okay. And there is one more term here, which is this term. So it is 1 times -1 to the power, the position, which is a first row and third column. And if I delete this row and column, I get this part, which is 0 minus 2, 5 minus 3. Okay. Now, I can do this computation, right? So if I do this computation, the first term is 4 times, what is the determinant of this matrix? Well, it is this part minus this part. So it is minus 12. Okay. And plus, I get the second part, 3 times minus 1 times, what is the determinant of this matrix? So it is a row of zeros, which means the matrix will have determinant 0. And finally, I have 1 times, what is the determinant of this part? It is 0 minus 10, which is 10. And if I do this computation, I will get this result, okay? So this is minus 48 plus 0 plus 10 gives me minus 38. Okay, so I could have done this easier because I could expand this determinant in any row I want, okay? So our theorem is true for expansion along any row, okay? And we will talk about later now that it's also true for expansion about any column as well. Okay, now what could be a better choice for this determinant? Well, if you look at the second row, these entries are already 0. So you don't need to compute their cofactors, because if you do them, you will multiply with 0 and it will give 0 contribution. Okay, so I have written here. So now I'm expanding along the second row. Now I look at this entry. So I'm multiplying by 0 the cofactor. The cofactor doesn't matter because once I multiply by 0, it will be 0. And same is true for this entry. So it will also give me 0, okay? This term will also give me 0, no matter what its cofactor is. So all the only term that's remaining is here is this minus 2. So what is the position? Minus 2 is in the second row and second column, so it will come with a positive sign. So this will be plus, times this number minus 2. And then what I do is, let me clear all this garbage here. What I do is I delete these rows and column, and then I get this matrix 4, 6, 1, 5. So it's determined this 4 times 6 minus 1 times 5. And I get the exact result. So I check that expansion along the first row and the second row gives the same result. Okay, let me stop here for your questions. Aklınıza gelenleri sorabilirsiniz arkadaşlar. Does this apply for 4 by 4 matrices? Yes, this applies to like n by n matrices. So general n by n matrices. But so let me give an example of 4 by 4, okay? But for easiness, I will write a matrix with a lot of zeros here. I don't want to write a matrix which has a row of zeros or a row of columns, because if I write that, the determinant is automatically zero. Okay, let's look at the determinant of this guy. Okay, we will use this cofactor method. So how does it work? So we look for a row or column, which is a lot of zeros. So we can either choose this column is ideal or this row is ideal. So whatever we want. So let us go on with, for example, this column. Okay, I didn't say anything about columns, but yeah, the expansion, you can also expand along a column. Okay, so you take each element in the column and you multiply it with its cofactor and then add them. That's also true. Okay, so let's go back. So let's expand along the first column. So what does this give? So this gives 4, because I have the first entry is 4. Then minus 1 to the power, the position of 4, which is 1, 1. And then I erase this. Let me erase a different color maybe. Erase this and this. So I get, in this case, I get this matrix. Good. Can we do this operation multiple times for the same matrix? I don't understand your question. So let me finish this example, okay? Let me finish this example, and if you still have questions, maybe we can talk. So, okay, so what did we find? So we started with 4 by 4 matrix for my form determinant. Now we have, so the rest are all zeros, right? Because the other entries are all zeros. They will not have any contribution to the determinant. Yes? Arada mikrofonu açıp yes falan diyebilirsiniz arkadaşlar. Kendimi çok yalnız hissediyorum burada. Okay.
Yes.
Thank you. Okay, so what are we doing? Okay, now you see, we reduced the determinant into a 3 by 3 case. Okay, so this is easier. Let me write this 4. Now this number is of course 1. And now I will have to compute the determinant of this guy. Now I can still use an expansion because this is just a determinant. Okay, now this is independent of here. So I can expand in this row, in this column, in this column, in this column, whatever suits fine. So let me cheat a little bit. Let me change the problem, okay? I don't want to do too much work. So I will erase this 2 and I will make this some number else. Let's make this 5, okay? Suppose this was 5. Then, no, I'm sorry. Suppose this was 0. So I don't want to do too much computation here. So if this is 0, then this is also 0. Okay, so just to make things easier, okay? So I cheated. Good. Okay, so if I do that, there's a suitable column here or a suitable row here, which both are fine. So let me carry on with this computation. Okay, now I'm going to compute this determinant using expansion along this row. So how does it work? Well, let me not change the color. So how does it work? So I'm choosing this one, which is 3, 1, and 3. Okay, so this is minus 1 to the power 3 plus 1 times this number is 1. Okay, times what I do now. I delete this row and look at this determinant, which is 1 times 1, 2, 1, 0. Why did I, okay. So this is just the first entry, and then I look at this other entries, okay? let me look at this number. So I look at these entries as well, but they're all zeros. So they will just give me 0 here. Okay. So finally, I reduce to 2 by 2. I can still use expansion. Expansion is still valid for 2 by 2 as well. Okay, but I don't need to do that. I already know what this is. So this is 4 times. Now this is 1. Okay, then I get 1 times 0 minus 1 times 2. So this gives me minus 8. Any questions here? Let me know.
-4 I think.
Sorusu olan var mı arkadaşlar?
Isn't that -4?
This one? This one?
No, no, this is the result.
The result is, this is 0 minus 2, so this is minus 2. Minus 2 times
Okay,
4.
okay. Okay.
Aubrey Drake Graham, who are you? Okay. So let me know if there are other questions. I hope you understand this method. When I'm deep. Okay, so we can combine row operations. So this row operation method to compute determinant is something we have seen yesterday, and we can combine it with the cofactor method to compute determinants. Okay, so how does it work? Is this a good example? I'm not sure. So let's just look at it. Okay. So find all values of t for which this equation is satisfied. Okay, so we have some t's inside this determinant. So again, we see there's a row here which has a lot of zeros, or we can use this column. Both are fine because there are a lot of zeros. So in the solution, I took this row. Okay. So if we do that, what do we get? So in this row, there is only one non-zero element, which is t plus 1. So this is t plus 1. And then I write its position as -1 to the power 3 plus 3, because this is in third row and third column. Times determinant of the remaining matrix. So I erase this part and I look at this determinant here. So it is this minus this times this, t minus 1 times t plus 2, minus 0 because there's 0 here. Okay. So I have, if I do this, I get the solution is t plus, so the answer is t plus 1 times t minus 1 times t plus 2 equals 0. So the solution is this. Okay. Okay, let me give you an example regarding this remark. Okay, so I said that we can combine row operations with cofactor methods. So let's recall the row operations as well. Okay, so let me give you an example here. So let's say that we are looking at let's say we have this 1, 2, and then I have -2 here, and then this is 0, this is 0, this is 4, and then let's write 1 here, let's write 2 here, and let's say 3 here. Okay, let's look at this 3 by 3 determinant. Now, one thing we can do is, okay, there is no row or column which has 2 zeros. So we have to compute 2 cofactors, but I don't want to do that. What can I do? Well, before starting, I can do this operation. Let's see. I can use this row operation, which is row 1, 2 row 1 plus row 2 to row 2. Now this operation we talked about yesterday does not change the determinant. Okay, so we talked about three row operations and we have seen their effect on the determinant. This was an operation which does not change the determinant, okay? So I can write this new determinant and they will be the same. So this is 1, 2, 1. Now this is 0. If I multiply this by 2, I get 4 here, and I get also 4 here, right? And this becomes 0, 4, and 3. Okay, so now you see I have a row of column of zeros here. There's only one non-zero entry here in this first column. Now I can use the cofactor expansion. So 1 is multiplied by the position of 1, and then I look at 4, 4, and 4, 3. Okay, so this becomes 4 times 3 is 12, and 4 times 4 is 16, so I get -4. So of course, for 3 by 3 matrices, doing such things does not make too much difference, but suppose you were asked the question about 5 by 5 matrices. These type of things really simplify the solution, okay? It lets you make less mistake, okay? So you could do this. Any questions about it? Anlaşıldı mı arkadaşlar burası? Var mı sormak istediğiniz bir şey? Bir dakika bekliyorum. Eğer anlamadığınız bir yer varsa.
Anlaşıldı hocam.
Teşekkür ederim. Okay, we have 10 more minutes. So in this last 10 minutes, let's start the discussion of finding the inverse of a matrix using the cofactors, okay? Now, we have a lemma here. So we have seen a method for computing the inverse of a matrix, okay? So you remember, let me just recall it for you. So we want to find the inverse of a matrix A. What we do is we write the matrix A, and then we write the matrix identity. And then we use row operations to find identity here. Try to make this into identity, and then what we get, if we can carry this out, we get A inverse on the right. Okay, so we did this like 3 or 4 weeks ago. This was one of the last topics we have seen in the class. Okay, now this is a good way of computing. This is the best way. I mean, this method is the best way to compute the inverse. Okay. So what we're gonna see is not that efficient, but this is some theoretical stuff, okay? Sınav nasıl yapılacak bilmiyorum. Cocoku 555. Gerçekten bilmiyorum. Siz ne kadar biliyorsanız ben de o kadar biliyorum sınav hakkında. Yani siz bana bilgi verin nasıl yapılacak. Yani herhalde bir aşamada insanlar bir araya gelmeye başlayacak diye düşünüyorum. Yani sonsuza kadar bu iş böyle gitmeyecektir. Okay, so now we will see a new method to compute the inverse of a matrix. So, okay, so this is a lemma which says that if so what is this? AI1. So this is the first element of the ith row, and this is the cofactor of AK1. And K and I are not equal, okay? So I'm using the cofactors of a different row multiplying them by AIs, okay? And this sum gives me 0 if I is not k. In the previous slide, we have seen this. So if I do this and I multiply it with the cofactor, its cofactor, then what I get is the determinant, right? So we have seen this formula and we applied it. So this is determinant of A. But you see, if these numbers are different, so this is k and this is I and k are not equal, this expansion gives me 0. So I have written a short proof here, but I don't want to. So let me just look at an example. Example will be better, okay? So you can read this short proof here. Okay, so if you don't understand it, we can discuss it. I think the proof is easy. So let's just do an example. Let's look at this matrix A. Let's compute the cofactors, these 2, 1 cofactor, 2, 2 cofactor, and 2, 3 cofactor. Well, they are just these numbers, these signs, multiplied by, for example, for A21, I erase this part and this part, so I get 2, 3, 5 minus 2, just like here, and I get 19. And same for the other ones. So now let's try to multiply these cofactors by elements from another row, not the row, second row, but another row. For example, the third row. Let's look at the third row. Okay, so the first element of third row is 4, and if I multiply it with this cofactor, and then I look at the second element 5, and I multiply it with this cofactor, and I look at this number and multiply it with the third cofactor. If I do this operation, I get 0. Same thing holds if I do expansion in the first row and use the cofactors of the second row. It again gives me 0. Okay, so this seems to hold. Okay, let me just say a few things about why this is true. I said you can read the proof, but I will say something about it anyway. Okay, so if we have a matrix B obtained from matrix A by replacing the kth row of A by its ith row, what I mean is I have this matrix A, okay, I have some rows, and so if I take this row, ith row, and write it, not swap it, but write it in the kth row, okay, so this is ith row, this is kth row. So if I have exactly two rows here, which are ith rows, if these 2 rows are identical, then I know the result will be 0, determinant will be 0, because if a row is a multiple of the other row, the determinant always gives me 0, because I can always obtain a row of zeros. Now, what this formula is saying is, this is computing a 0 determinant because it's computing the determinant of a matrix which has exactly 2 identical rows. That's the reason this gives 0, okay? You can convince yourself about this. I urge you to write up some examples and look at it. So what you're really doing is computing a determinant with identical rows, 2 identical rows, okay? So that's why it gives 0. Okay, this is very good. This is very good. So what did we obtain? So, okay, we obtained something interesting. So we defined something called the adjoint matrix. Okay, this is not easy to compute. It requires a lot of computations, adjoint matrix. So this is actually just theoretical stuff, not used in real practice. But of course, it's used for proving other things. So it's important. So how do we compute this adjoint matrix? Well, we compute the cofactor of A11, which is the capital A11. We have seen how to do this. Muhammed Özen, what does this have to do? We will just see this now. Hocam kitaplar yeşil ekran mı yoksa gerçek mi? Kitaplar yeşil ekran mı? Ne demek o ya? Yoksa gerçek mi? Anlamadım sorunu. Ha evet. O şeyler kütüphanemdeyim şu anda. Beğendin mi? İstediğin kitap varsa verebilirim. Okay. So iyi bakın. Oradaki güzel kitaplar olması lazım arkadaşlar. Gelecek şeyde başka bir yerden yayın yapacağım. Tamam. Tercih ettiğiniz yeri söyleyin. Daha böyle tropik bir yer olabilir. Daha güneşli. Eyfel Kulesi mi? Uzay güzel fikir. Uzay arka planı. Tamam, uzaydan yapmayı düşünüyorum arkadaşlar. Gelecek dersimiz uzayda olacak. Değişik mekanlarda yapmanın faydalı olacağını düşünüyorum. Okay, let me just finish, okay? We can do gate later. So, okay, adjoint matrix. So it requires a lot of computation, as I said. You compute each cofactor here, so you have to do like n squared cofactor computations here, and then you come up with a matrix, and then you take its transpose. And then what this line means is, so this line is exactly the same thing as saying that the matrix A times its adjoint matrix gives me determinant of A times identity. And same for this line, okay? Just look at this. This is very important identity here, okay? So there is something interesting. So if the determinant is not zero, then what we can do is we can take this determinant to this side, which gives me A times 1 over determinant times adjoint of A is the identity. So this is the relation for the inverse matrix. I think this is very cool. So this is really the inverse matrix. So to compute the inverse matrix, a method is computing all the cofactors, taking the determinant, taking the transpose, and then dividing it with the determinant of A. If we do this, we end up with this inverse matrix. Okay, so I'm not sure if I have time, so I just have 2 minutes. So I suggest you do this example on your own, okay? So take this matrix, compute all 9 cofactors, okay? You have to compute all the cofactors, A11, A12, A13, blah, blah, blah. All 9 of them. And then you will take the transpose of this, and you will come up with something called adjoint of A. Okay? And then you will compute the determinant, and you can verify this identity easily, okay? I suggest you do this. If you can't do this, next time I will start with here. Okay, everybody, I think that's it for today. So okay, I also have the answer here. Okay, I think we're almost finished with this section. So we will finish this chapter next time. So we just have a few things left. So we will finish this chapter. So, okay. Any questions? Evet arkadaşlar, söyleyeceğiniz varsa bir şeyler söyleyebilirsiniz. Yoksa dersimiz bitmiştir. Gelecek sefer tekrar sanıyorum invitation, yani davetiye göndermeme gerek yok. Sanıyorum aynı link üzerinden bağlanabiliyorsunuz arkadaşlar. Yanlış mı biliyorum? Doğru biliyorum değil mi? O şekilde olması lazım. Yani aynı koddan gene ben de aynı kodu kullanacağım. Orada gene buluşacağız. Yeni bir şey yapmıyorum. Taylan Hoca Fan Club. Teşekkür ediyorum. Ben de sizleri seviyorum arkadaşlar. Görüşmek üzere. Sorunuz olursa her zaman yazabilirsiniz. Çalışırken aklınıza takılan bir şey olursa görüşürüz arkadaşlar. Şimdi video şeyini kapatayım.